All right, welcome everyone. We have Martina Conte from HHU Düsseldorf speaking today. And the title of our talk is Definability of the Rank and the Dimension of p-adic Analytic Pro-P Groups.
Thank you very much for the invitation and the opportunity to speak. So I want to mention first that what I present today is joint work with my advisor, Benjamin Klopsch, and this will be part of my PhD thesis. And also a preprint should be available quite soon. So as you said, the title of my talk is Definability of the Rank and Dimension of p-adic Analytic Pro-P Groups. And I added also more generally of Pro-Pi groups, because what we actually proved is that rank and dimension of Pro-Pi groups are characterized by a single first-order sentence in the language of groups. I will explain all of these words during my talk, so don't worry if you don't know some of them. And I will start with the first important step of Pro-P groups. So recall that Pro-P groups are inverse limits of finite P groups. For example, you can think of the additive group of p-adic integers, that is the inverse limit of the group Z modulo P and Z, where n runs over the natural numbers. So p-adic analytic Pro-P groups form a particularly nice class of Pro-P groups because they have an analytic structure, but also purely group theoretic characterizations. So let me start by recalling one group theoretic characterization of these groups. In order to do so, I need to recall what uniform Pro-P groups are. So first of all, a uniform Pro-P group is topologically finitely generated. So in my talk, when I will say finitely generated, I will always mean topologically. So elements A1 up to AD topologically generate a Pro-P group G if the closure of the abstract group that they generate is the whole of G. So a uniform Pro-P group, as I said, is first of all finitely generated. And it has the following properties. So it has many pth powers. So in which sense? In the sense that the commutator subgroup of G is contained in the group generated by the pth powers of G if P is odd. And the commutator group of G is all contained in the group generated by the fourth powers of G if P is equal to 2. So this is what is called a powerful Pro-P group. So uniform Pro-P groups are powerful, and moreover, they have the following property that might give a reason for the term uniform, is that we can consider the iterated Frattini series of these groups. So recall that the Frattini subgroup of a finitely generated Pro-P group has this form. So is the group G to the P times the commutator subgroup of G. And then we can iteratedly apply this Frattini. So take the Frattini of the Frattini and so on and so forth, and get the so-called iterated Frattini series of G. Well, if we consider such series, then we have the cardinality of the quotients. So the quotients phi minus 1 of G over phi plus 1 of G are all constant, or phi of G, I'm sorry, are all constant and hence equal to the cardinality of G over phi of G. So what is an example of uniform Pro-P groups? Uniform Pro-P group. We can start with GLDZP, the group of invertible D times T matrices with entries in ZP, the p-adic integers, and by simplicity, I consider P a node prime. And then we can consider the principal congruent subgroups of this group. So given a natural number I, we can consider GLD IZP that consists of the matrices A in GLD ZP that are congruent to the identity modulo P to the I, where here I mean that I consider the reduction of every entry of the matrix modulo Pi. With this group, we can form a descending series of GLDZP, and it turns out that the first principal congruent subgroup GLD1ZP is a uniform pro-P group, and that these other principal congruent subgroups form the descending Frattini series of this group, and in this case, this constant index that we have in the definition of uniform is p to the d square. So whenever I say uniform pro-P group, you can think of this group GLD1ZP. Now, thanks to these groups, we can introduce the first characterization of p-adic analytic pro-P groups that I want to recall. That is due to Lazar, Lubotsky, Mann, and Segal. And it states that the pro-P group is p-adic analytic if and only if it is finitely generated and has a uniform subgroup of finite index. So again, when I say, thanks to this characterization, when I say p-adic analytic pro-P group, you can think of this principal congruent subgroup if you want to have a group in mind. But let me give also another group theoretic characterization of these groups that allows me to introduce the first invariant that I mentioned in the title, which is the rank of a pro-P group. So given a pro-P group G, I denote with D of G the minimal number of generators of G. Then the rank is defined as the supremum of D of H, where H runs over the closed subgroups of G. So this means that the rank is the minimal number, let's say R, such that every closed subgroup of G can be generated by R elements. We have the following characterization of analytic pro-P groups. So a pro-P group is p-adic analytic if and only if it has finite rank. So again, this is a really strong characterization, and from now on I will talk at the same way, in the same way of p-adic analytic pro-P groups or pro-P groups with finite rank, because these are the same thanks to this characterization. Okay, so I said when I presented what I was going to do, that we want to show that the first, at least that the rank of a pro-P group of finite rank can be characterized by a single first order sentence. So let me recall what this means. So first of all, what the language of groups is and what first order formulas in the language of groups are. So the basic idea in model theory is that we have a structure. We distinguish functions, relations, and elements, and we want to have a language with which we can talk about these structures, these functions, relations, and elements. So For example, what do we have when we have a group where a group G is a set endowed with a binary function, so the group operation, a unary function that is the inverse map, and finally a distinguished element, which is the identity element of the group. So by looking at this, we see that when we want to talk about groups, we can consider the language of groups that is exactly built with these three symbols. So a symbol for the binary operation, a symbol for the unary operation, so the inversion, and a symbol for the identity element. And okay, so what is now a formula in this language? A formula in the language of groups is a finite string of symbols that is built using symbols from our language. So one of the three symbols in this set of the language of groups. Then symbols for variables that I will call X, Y, and so on. Then we have Boolean connectives, so or, and, not. Then we have quantifiers, so exist and for all. We can use parentheses, and we can use the equal sign. For example, let's see immediately some examples of formulas. We can have this formula. There exists X such that X times X times X is equal to the identity E. So you see that here I'm using just a symbol X for the variable. In existential quantifier, there exists the equal sign and the identity. So from now on, we will simplify such notation and write just X to the third in such a situation. Another example might be X squared is equal to E. Final example, let me call it gamma, is the one that says for every Y and Z, the commutator of Y and Z is equal to the identity. So these are all examples of first order formulas, but I always mentioned sentences, not just formulas. So what sentences are is they are specific kinds of formulas. So a sentence is a formula in which all variables are inside a quantifier. For example, if we look at our three examples before, we see that 1 and 3 are sentences. If we are given a sentence phi, we will use this orange symbol here to say that G satisfies phi whenever phi holds true in G. For example, G is an abelian group if and only if G satisfies the sentence gamma in the previous example. Let me also just give another a last remark that is that in first order logic we can quantify only over elements of the group and not over subsets or subgroups. So we cannot say there exists a subgroup with certain properties, and this is making things let's say harder. Okay, so we now have all the, let's say, tools to start talking about the problem of the rank. So where does this problem come from? As I said at the beginning, we want to express the rank of p-adic analytic pro-p group with a first order sentence. This problem comes from a recent paper of Nies, Segal and Tent, where they started studying the finite axiomatizability of profinite groups. So which profinite groups can be characterized up to isomorphism with a single first-order sentence. And among many results contained in this paper, one can find also this proposition regarding the rank of propy groups that states the following. For all natural numbers R, we can find a sentence rho PR in the language of groups, such that for a propy group G, if the rank of G is bounded by R, then G satisfies such formula rho PR. And conversely, if G is a propy group that satisfies this formula, then its rank is bounded by a function of R. So this is the specific function is R times 2 plus log 2 of R. So a natural question arises whether it is possible to find a sentence that actually characterizes completely the rank, so that gives us an if and only if. And we found that this is possible. So we found a sentence sigma PR such that the propy group G has rank R if and only if G satisfies this sentence sigma PR. So I would like to give a vague summary, let's say, of the proof. First of all, I want to introduce what is the key tool of this proof. This is a result, a group theoretic result that is also interesting in its own, and that allows us to detect the rank of a propy group G in a finite quotient of G. So we can find a finite quotient of G that has the same rank as G. Specifically, so we have the following result. If G is a propy group whose rank is bounded by some natural number B, then we can always find a powerful subgroup of G of finite index. And this is because of the characterization of propy groups of finite rank, or equivalently p-adic analytic propy groups that I gave at the beginning. So the rank of G is given by the rank of the quotient of G by the iterated Frattini 2b plus 1 times of F. So we have our group G, we find our normal powerful subgroup, and we can then go down to this term of the iterated Frattini series of F. This will be a finite quotient, and the rank of this quotient is the rank of G. Okay, I will not discuss the proof of this theorem because it's a bit technical, but we will use this tool later. Also, before I get into the proof for showing that there is this sentence that characterizes the rank, let me just note that when we talk about subgroups of a given group in model theoretic terms, we cannot just talk about any given subgroup, but these have to be definable subgroups. So a definable subgroup is a group for which belonging to the group is expressed by a first order formula. So H is definable if there exists a formula K such that H is made of the elements X in G, such that G satisfies this formula K of X. So let me give an example of this. If we consider the center of any group, well, this is made of the elements X in the group, such that for every Y, XY is equal to YX. So you see that this condition is a first order formula. And so the center of G, so the center of a group is always a definable group. A key point let's say, when working with pro-P groups, in particular with finitely generated pro-P groups, is that their Frattini group is definable, thanks to the fact that the commutator subgroup of a finitely generated profinite group is definable. So we will often find iterated Frattini, and we will be able to talk about them and also about quotients by these groups because they are definable. We could not talk about any group. So I can now give an idea of the proof of the fact that there exists a sentence that completely characterizes the rank. And I will actually give, let's say, the ideas of how to construct such a sentence. So let's start with G, a pro-P group with rank R. Now, by the theory of p-adic analytic pro-P groups, we can find a normal subgroup F in G. So F will be an iterated Frattini of G, iterated by a number that depends on the rank. That has some good properties. So is definable. It is powerful. So these are these groups that I was talking about at the beginning, for which the commutator subgroup is contained in the group generated by the pth powers. The rank of F is bounded by R. And if we consider the quotient G over F, this is a finite quotient with rank bounded by R and order bounded by P to a function of R. So now we can see that we are able to express all of these properties by first order sentences because we can express powerful by a sentence alpha just by looking at the definition of powerful subgroup. So because, as I said, the commutator subgroup is definable, and we just have to say that this commutator is contained in G to the P. We can talk about this finite quotient G over F because here it's just enough to say that this quotient must satisfy the multiplication table of a finite group that has this bounded order and this bounded rank. So we can find a sentence beta that expresses this property. Finally, we are left with rank of F bounded by R. Well, but this we can also do because for powerful pro-P groups, the rank is the same as the minimal number of generators. And there is a sentence already used in Nies, Segal and Tent paper that allows to express the number of generators of a finitely generated pro-P group. So let's say that we find this sentence gamma. If now we put these three sentences together, so let me say more or less a sentence that is made by the join of alpha, beta, and gamma. So alpha and beta and gamma, even if we should take into account that we are talking about quotients and subgroups, so would not exactly be this join, but for this talk, it doesn't matter. So now we have this sentence that is certainly satisfied by a pro-P group of finite rank, because this just tells us that we find a normal powerful subgroup that has bounded rank by R, and such that the quotient of G by this group F as such bounded order and bounded rank by R. Okay, what happens on the other hand if we have a pro-P group G tilde that satisfies such a sentence phi? So if G tilde satisfies phi, we now by the sentence can find a powerful subgroup F tilde with rank bounded by R. And so the rank of G tilde by a general result on the rank is bounded by the rank of F tilde plus the rank of the quotient G tilde over F tilde. And this is bounded by 2R because each of these is bounded by R. So now we actually want to have a sentence that tells us that the rank is exactly R, but here we have a bound already on this rank. And so we can use our key tool that was telling us that if we have a pro-P group with bounded rank by a certain number B, then if we take a finite quotient that depends on this bound B, we can find the rank, the exact rank of G. So what we need to add at our sentence is just a small other step that tells us that the rank of the finite quotient G over the Frattini subgroup, this will be a 4R plus 1 of F is equal to R. So now if we put together phi and epsilon, we have, again, more or less the required sentence sigma PR. So here we are done as far as the rank is concerned. In the title, I also mentioned the dimension of p-adic analytic pro-P groups. So what is this dimension? As I said at the beginning, if G is pro-P p-adic analytic or equivalently pro-P of finite rank, then we can find a uniform subgroup of finite index in G, uniform, and we can consider its minimal number of generators, D of U. It turns out that this number does not depend on the choice of U. So if we choose another uniform subgroup of finite index in G, this number will be the same. So we define the dimension of G to be this common number D of U, where U is any uniform subgroup of finite index. It turns out that this number is the same as the dimension of G as an analytic manifold, but this is a completely group theoretic description of this. So since we talked about the rank, it is natural now to wonder if this number is also definable, and it actually is. So for every R and D, we have a sentence delta depending on P, R, and D in the language of groups, such that for a pro-P group G with rank R, the dimension of G is equal to D if and only if G satisfies the sentence delta P, R, D. Again, let me just give an idea, a vague idea of the proof. We start with the abelian case. So in the abelian case, G will be isomorphic to ZP to the D times the torsion part, so Cp to the K1 times Cp to the Ks for some S. And this by the structure theorem of abelian pro-P groups. Now the dimension of G is equal to D, the exponent of Zp, and the rank of G that we called R. One can see that the rank of G is the number of factors in this direct product. So it is D plus S. So we see that G has dimension D if and only if it contains a subgroup isomorphic to S, that is R minus D copies of Cp, and G does not contain a subgroup isomorphic to R minus D plus 1 copies of Cp. And this can be expressed with a first order sentence, because we just need to say there exist P to the R minus D elements that satisfy the multiplication table of this first group, and there do not exist P to the R minus D plus 1 elements that satisfy the multiplication table of the second group. So this is easy. Let's now look at the general case. Again, let's start with G, a pro-P group of finite rank R and dimension D. We consider the adjoint representation of G. So from G to GLD QP, this is the representation induced by conjugation. And we look separately at the kernel and at the quotient by the kernel of this map. So first, let's look at the kernel. Let's say K kernel of the adjoint representation. This is actually definable because this will be the centralizer of a uniform subgroup of G. So similarly to the center, also the centralizer is definable, and so we can talk about this subgroup. And moreover, K contains an abelian subgroup that is definable and has the same dimension as the dimension of K, and has the dimension of K. And this will be the center of K, actually. So now we can just use the abelian case and recover the dimension of this subgroup that is also the dimension of K. And so we are done for this part. We now look at the quotient of G over K. So the dimensions of these two bits added together will give us the dimension of G. So we now look at this quotient. And so we find, again, a powerful, definable subgroup F bar, let's say, in G over K. This again will be an iterated Frattini subgroup. We can consider the quotient of F bar by its torsion subgroup. So this is actually uniform, is a uniform group, and has the same dimension as G over K. So with dimension equal to dimension of G over K. So again, if we are able to express the dimension of this quotient, we will be able to express the dimension of G over K. Now, if we want to talk about this quotient, actually distortion of F bar should be definable. And this is true thanks to the fact that G over K is linear, so this embeds in GLD QP, so we can talk about this quotient. And moreover, we can express the dimension of uniform groups. And this is because for uniform groups, again, the dimension is equal to the minimal number of generators. And as I said before, we have a sentence for the minimal number of generators of a finitely generated pro-P group. And so we can do this. So now, finally, if we put these two cases together, we find the dimension of G expressed via a first-order sentence. Conversely, if a group satisfies this sentence as at least this dimension, but since the dimension is bounded by the rank, we can impose that this is actually the dimension. So the important part is that one divides into these two cases and use the abelian case. So this gives an idea of the dimension of the proof for the dimension. Let me now go at the, up to now we just spoke about p-adic analytic pro-P groups. So let me talk about some more general groups. We consider pi a finite set of primes, so P1 up to Pk. We start by considering direct products of the form G1 up to Gk, where each Gi is a pro-Pi group. So these are just direct products of finite direct products of pro-Pi groups. And these are called CPI groups in the paper of Nies, Segal and Tent. They also study this kind of groups. One can see that in this case, the rank of G is given by the maximum of the ranks of the factors in this direct product. And what could dimension mean in this case? Well, in this case, we consider what we could call the dimension vector of these groups that has in each component the dimension of the corresponding pro-Pi group. So what we showed is that also in this case, rank and dimension can be expressed by a single first-order sentence. So this case is not trivial. Let's say there is some work to do because it's not trivial to go to the pro-P part of these groups, but still it uses similar ideas as before. And let me also say that we actually prove also that all the vector with the ranks, so where each component, the ith component, has the rank of the ith factor in this direct product is defined by first order sentence. In this case, so when we have groups of this form, these factors G1 up to Gk, these are the pi or pro-pi C-loss of G. So a pro-pi C-law of G is a maximal pro-pi subgroup, and the theory of the C-law theory for finite groups extends similarly to this to the case of profinite groups. This gives us a hint when we want to consider even more general groups. So these more general groups that we want to consider are pro-pi groups. These are inverse limit of finite pi groups. So I recall that a finite pi group is a finite group whose order is divisible only by primes in the set pi. So if you want an example to have in mind for this kind of groups, you can think of GLD ZP. So before we were looking at the first principal congruent subgroup in the pro-P case. Here you can think of all of GLD ZP. So what we prove is that also in this case, the rank is definable by so there is a single first order sentences that completely characterizes the rank. The dimension vector, so the vector that has in the ith component the dimension of the pro-pi C-law of GLD-ZP, and also similarly of the rank vector. So I still have 5 minutes, so maybe I can give just very quickly.
Can I just say you have 8 minutes, not 5.
Okay. So I can give a sketch of the proof of this result. So the main point here is the following. If we start with the pro-pi group G with rank bounded by R, thanks to a result that uses the classification of finite simple groups, we can find a subgroup K that has the following features. So K is C-pi, so this meant that it is the direct product of pro-pi groups where pi is a prime in this finite set pi. And moreover, the index of K in G is bounded by a function of pi and R alone. Okay, this uses the classification. And now this K is will not in general be definable, but we can find a subgroup of K. So if I have again, here there is K. We have a subgroup that I call H, that is G to the F pi R, that is definable. It is again a C-pi group, so it is again of the form H1 times HK, and moreover has rank bounded by R. And if we look at the quotient of G by H, we have that the order of this quotient is bounded again by a function of pi and R alone. And the rank of this quotient is also bounded by R. So again, we are a bit in a similar situation to the one we had for pro-p groups. So remember, for pro-p groups, we found a subgroup that has bounded rank by R, such that the quotient has rank bounded by R. And so let's say that this gives us a sentence eta pi R that will tell us that a pro-pi group has rank bounded by 2R in total. But we want to say that G has rank exactly R. So we would need something like the key tool that we had in the pro-p case, and that allowed us to see the rank of G in a finite quotient of G. And indeed, we could find this result also for pro-pi groups, even if in this case, in this general case, the result uses results of Lucchini that require the classification of finite simple groups. So if we start with the pro-pi group G, as we are in our situation, we have a C-pi subgroup H, so a subgroup that is the direct product of pro-pi groups. And now we go down to a subgroup of H that is, again, such a direct product in which each factor of the direct product is powerful. Now, if we go even more down, we take the an iterated frattini of the subgroup F, where this B, the number of iterations, will depend on the bound of the rank. Well, this is a finite quotient, and again, the rank of G is equal to the rank of G modulo such iterated frattini. So again, we have let's say a finite group that sees the rank. And so we can, by using this tool, we can conclude the proof as we did in the pro-p case. So we can add a bit to our sentence that was for now stating that a pro-p group has that satisfies this sentence has rank bounded by 2R, and impose in this sentence that the rank of the finite quotient G over the iterated frattini of the subgroup F is exactly equal to R. So put in the sentence that we had before, I called eta PR this, and epsilon together, we get the sentence that tells us that the pi group G has rank R. As for the dimension is concerned, so here, since H has finite index in G, actually the vector of dimensions of H is equal to the vector of dimensions of G. And so we can just look at the group H and use the C-pi case to state what the dimension is via first order sentence. And yes, so this is everything I wanted to say. So thank you for listening.
Thank you very much, Martina. Can we all please unmute ourselves and give the speaker a round of applause? Okay, if you have any questions for the speaker, please ask them now. Yeah, Fabian.
Maybe I can start. So the dimension is obviously also a geometric. I mean, it has a geometric interpretation. So can you also, for the rank of a p-adic analytic group, express this in terms of the geometry?
I actually don't know. So this is what is called the proof rank. So there are also other notions of rank. This that is about the number of generators of subgroups is this proof rank. And I don't know of any geometric interpretation of it. I don't know if someone else can say something about it.
Yeah, thank you, Fabian.
Maybe if you allow me a second question.
Yeah, please go ahead.
So can you go to this place where you defined for us gave us the definability of the Fratini subgroup?
Yes.
There was something that I didn't
Yeah.
understand. Here. So did I get this correctly, that the commutator subgroup here is definable?
Yes, exactly. This is the point, that for finitely generated pro-p groups, this is a result on the width of the commutator subgroup. So if G is generated by A1 up to AD, then the commutator subgroup of G is equal to this set. And hence it is definable. So you can say these are the elements for which there exist x1 up to xd. Once you are given the generators for which you can write the element as such a product.
So every element can be expressed by at most d commutators. That's kind of the thing.
Yes, so if G is generated by d elements, so you are given these d generators, then the commutator subgroup has this form.
Okay, I see. Thank you.
Thank you, Fabian. Any other questions? Let me ask a very extremely naive question. What's beyond pro-pi groups?
For example, one might consider, so this is more related already to the pro-p analytic case. One might consider more general analytic groups, like R analytic groups. So this might be another class of groups to consider, for example.
Right. So like in the paper by, what are the names? Nies, Dan Segal and Tent, they have these negative results. So the groups for which like they get the negative results, I'm guessing, are still not applicable, are still not like suitable for like your treatment.
So now this is yes, more about the finite axiomatizability. Yeah. So if they can be, if the group can be characterized up to isomorphism by a first order sentence. Yeah. So this is still related. So it's in this framework of studying properties of profinite groups in this model theoretic view, but it is slightly different question.
Yeah. I mean, I was just wondering if, one could define this rank and dimension for those groups. But yeah, okay, of course.
Okay, these I should look into.
Yeah, it could very well be a very uninteresting thing to do. Okay. Any more questions? Also, can you send these slides to me later? I mean, not the slides, I mean the notes.
Yes, yes, of course.
Okay, in case we have no further questions, let us thank Martina again for this very wonderful talk.
Thank you very much for the invitation again.
Yeah, not a
and
problem.
to you all for listening.
Yes, thank you all for coming. It was really a pleasure. Let me stop recording now.